So this video is actually usually tends to be one of the more interesting videos that we do because it finally reconnects some ideas that we learned about in Calculus 3 to what we are doing in Calculus 4 with double integrals. And what we're talking about is finding the surface area of some 3D function, of some 3D shape as it exists over a 2D region. So what are we talking about? We're talking about, let's say we have some function, right, some function f of xy, and I want to know what the surface area is of this shape, over some particular region. So let's say I want to know the surface area of that particular chunk right there. Maybe I'll highlight it in blue for us. Get a nice little shade. So I only want the surface area of that piece of our function right there as it exists over this region of integration. Okay, this exact region of integration right here. Okay, I'm going to call this D. And so the question is, how do we find the total surface area, right? How do we find total surface area of our little chunk that we care about? Well, hopefully you have all picked up by now that I like to take the approach that in order to find the total amount of something, right? What thing means that we're going to add up a bunch of things to get the total, right? It's the integral, and we're going to add up a whole bunch of essentially tiny surface areas. Now, why can't we just approach this all in one go? Well, because this shape is very much so curved, and I have no idea how to do this, right? I drew also, by the way, a nice little rectangular-ish shape, but our region of integration could be something that looks like this, and it could yield, some surface area on our shape that looks like this, right? And so coming up with the surface area of that is quite challenging. So where does Calculus 3 come into play in this example? Well, in Calculus 3, we saw that we could construct. Actually, here, let me before I go this. How do we come up with tiny surface areas? That's what we're talking about. We're talking about at a particular point. You give me an input point. We go all the way up to the proper output. How do we come up with a tiny surface area at this point, right? What is, tiny? I want the tiny surface area associated with this point, this tiny little surface area. Okay, that bit right there. It turns out that calculating it can be kind of hard. And so what we did in Calculus 3 is we learned about these things called tangent planes, right? So we learned about these things called tangent planes. Sorry about that. And we use tangent planes to create small, tiny approximations of that little region there, of that purple region. We use the tangent plane to create a small approximation at this point, okay? And how we did this in Calculus 3 was at a very finite, tiny little level. What we did is we created these tangent. I'm going to draw them a little longer than what they actually are, right? If they're on a microscopic level, they're only supposed to be this long, but just for illustrative purposes, we have two tangent vectors, okay? We have one tangent vector that we get from taking the partial derivative with respect to x, and we have another tangent vector that we get from taking the partial derivative with respect to y. And hopefully from Calculus 3, we remember that if we want to determine the area of the region that's basically created by this little parallelogram, if we want to calculate this particular area, the way that we do that is magically let's say that this little brown vector is the vector v, and then the yellow vector is this vector w. Then the area of the parallelogram that's created between those two is the magnitude of the cross product of those two vectors, it turns out. Okay, that's all we have to do. Now you may remember that for any function f, there is a tangent plane, and that tangent plane was the result, right? It has a tangent, or it has a normal vector, right? Every tangent plane has a normal vector, and that normal vector came from doing the cross product of something that had to do with the partial derivative of x and the partial derivative with respect to y. Okay, this is way back in Calc 3. So I'm not going to deep dive all of it, but what I will do is show us how we're going to come up with these tiny surface areas. That's basically going to give us our formula, because we're like 90% of the way done. We have double integrals. We're pretty much done. We just need to come up with that little formula. And so it turns out that that little vector v, that little tangent vector v over there, our little tangent vector in the x direction, well, it had an x component of dx. Okay. And it has no change in the y direction, so no y component. And then in the z direction, we would have dz. Okay, we have some change in the z direction, right? That is this vector. We have some, let me zoom in and I'll erase some things to hopefully kind of clarify why this is the way that it is, right? So we have our tangent vector, and it comes as a result from the change in x, right? There's our dx, and our change in z, our dz over there. That's how we get this vector, okay? And there's no change in the y direction. There's no y component to this vector, okay? Now, in the same vein, our little tangent vector w over there has no change in the x direction, but it definitely has a small change in the y direction and some change in the z direction. Now, you might notice and say, hey, they both have dz. Okay, what can we do with that? Well, technically, I'm tricking you. All right, these dz's are not the same. You're like, Dylan, what do you mean? Well, because if I go in the y direction, the dz amount could be way different than if I go in the x direction, right? I could be going down if I go for a walk in the y direction. I could be going up if I go for a walk in the x direction. Hope I didn't mix those up. And so the way that we clarify which dz's these are is we don't write it like this. What we do write instead, however, is I'm going to write it as the partial of f with respect to x times dx, right? Times dx, and the partial derivative of f with respect to y dy, okay? And what this does for us, right? What this does for us is it basically clarifies, oh, this is my dz as it relates to the x, and this is my dz for the y direction. It basically specifies it for us. Okay. Now, hopefully, also we are familiar with the notation f sub x and f sub y. So I'm actually going to just rewrite this as f sub x dx and f sub y dy. And just to make sure that we're all on the same page and we're not getting super lost, the whole point of this is that at any single point on our 3D function, we can construct two tangent vectors, and all I need to do is to find the area of the parallelogram between them, which this is all happening on a microscopic level, right? Remember, it's just drawn large to help you all visualize it. But we'll find the area of that parallelogram, which comes from calculating the determinant of the cross product of those two vectors. Okay, that's a calculus 3 topic. And so what do we get to do with this? Well, now we're just going to do our calculation, and hopefully this leads us to our formula. So what I'm going to do first is I'm just simply going to calculate the cross product of those two vectors. So I, j, k, right? This is going to be the cross product of these. And then we'll put in our dx, 0, and then f sub x dy. And then for the second one, we'll put in 0 dy, and then f sub y dy. Oh, I made a mistake in the first one. This should be f sub x dx. Whoops. Dx. Okay, cool. And so we're going to come up with our new vector, which hopefully, remember, when we do the cross product, we're going to get something with like an I minus something with a j, and then plus something with a k, right? And this will be our new vector. So how do we go about doing this? Well, let's see, we start off by doing this right here. And so we take the determinant of what's left over. So we do 0 minus what we get over here. So it looks like we're going to get a minus f sub x and then dx dy for our I components. Then we go ahead and do this again, but we do it for the middle one. And so here now we're going to get dx times f sub y dy. So I'll write that down. So f sub y essentially dx dy minus 0, right? Because when we go this way, we just get a minus 0. So nothing too exciting happening there. So that's our second component. And then doing the very last one for the k component, we're just going to get a very fancy dx dy, and again 0 if we were to do the subtraction on the other diagonal. So that's determinants. So if you don't remember those, definitely review how to take the determinant of something, how to take a 3x3 determinant, all that good stuff. So what we just found out is that when we look at our 3D function and we pick a point on it and we calculate the normal vector, which is what we get when we cross v cross w. If we calculate the normal vector at that point, what do we get? Well, we get the vector negative f sub x, dx dy, negative f sub y dx dy, and the vector component dx dy. Boom, there's our vector. Now, dx dy, by the way, represents like our dA, right? It's some small change in area. This is just some quantity. It's not something we're calculating. Every single component has it. I'm going to go ahead and factor it out, okay? So this is the vector negative f sub x, negative f sub y, 1, multiplied by dx dy, big whoop, okay? It's some value. Well, how do you come up with the magnitude of this, right? If this is v cross w, then the magnitude, right? Then the magnitude of v cross w. Well, hopefully we remember how to take the magnitude of a vector. It's just going to be for us f sub x squared plus f sub y squared plus 1. And then what's the magnitude of dx dy, which is just some value? Well, the magnitude of a number or a value is just the value. So this is just going to be dx dy on the outside, which, by the way, if you're feeling a little spicy, you can just call this, and the textbook just calls this dA, which hopefully by now we should feel a little comfortable with. So what have we done? We basically found that for our surface area formula, which is adding up a whole bunch of infinitely small surface areas, okay, that what this formula just evaluates to is we're going to add up over our region of integration, which we'll call D. Okay, so we zoom out to our photo, right? This is our region of integration. We're adding up a bunch of tiny surface areas given by the formula f sub x squared plus f sub y squared plus 1 with a little dA at the end. And it turns out this is our really, really, really nice formula for surface area, okay? So it's not really a hard formula to memorize or really a hard one to calculate. It does require that we remember that at any point, right? It requires us that we remember this, right? It requires that we remember that at any point we can calculate two tangent vectors, and those vectors, you just take the cross product and then their magnitude, and you get a tiny little surface area, okay? This is from, if you are interested, you can look in the textbook. It's going to be on the section in the textbook on tangent planes, I believe chapter 14. Okay, so let's do an example, right, to really drive this point home. So for example, find the surface area. Find the surface area of z equals x squared plus 2y over the triangular region, right, bounded by, we'll say 0, 0, I'll just make some easy points, 1, 0, and 1, 1. Okay, so let's figure out what to do. So the first thing I would do is attempt to draw a sketch. and more importantly is going to be this region of integration. So here's 0, 0, here's 1, 0, and here's the point 1, 1. Okay, so well, maybe I'll put that in a little better spot. So 1, 1. Okay, so here's our region of integration. This little right triangle right here. Okay, there it is. Now, what's our function look like? It doesn't really matter what our function looks like. Okay, our function exists something like this, and we're trying to calculate the surface area of the piece that exists kind of above this shape, right? So we're trying to calculate this surface area right here, that piece right there. Now, what does this shape actually look like? Okay, how do you do this? This is an example. This is a good exercise in doing traces. So you can let x equal 0. That gives us z is equal to 2y. If you do y is equal to 0, this gives us a parabola, z equals x squared. And if you do z is equal to 0, this is going to give us the cut of y is equal to, with a little rearranging, negative x squared over 2. So we're looking at two parabolas on one side, and then we're looking at lines on the other. So I believe this is going to be kind of like a parabolic cylinder of sorts. And if we're not sure, we can go to GeoGebra. Right, you can bust out GeoGebra. Here it is, right? And so sure enough, if we look down, there's, here's our one parabola looking down at it. This is the parabola, y is negative x squared over 2. Here's going to be our line that we see if we look at it sideways, right? There's z is equal to 2y, so on and so forth. And so we're basically just calculating the surface area of a piece of it, but that's not really, the important part. The important part is that we understand that, we have a formula. And I'm not a big, memorized formula person. All I know is that we want to add, we want to find the total surface area. Okay, total surface area. And to do that, we can basically add up a bunch of tiny surface areas. And to do that, basically we already evaluated the formula, but we're going to do a double integral over our region of integration, d. We can call this d if you want. And then we have the little formula that we got from doing the magnitude of the cross product of the two tangent vectors that we get at any single point on our shape with a little dA at the end. So this isn't so bad. Let's do some calculations. So first off, f sub x, since our function is z equals x squared plus 2y, f sub x here is going to be 2x, and then we square it. What is our f sub y? F sub y here is just going to be 2, and we square it, and then there's nothing to do with the 1. So this equation, right, without doing much to it, is the double integral over d of the square root of 4x squared plus 5 dA. And so the only thing that's left to do is to figure out our bounds, but looking over here at our shape, the bounds should kind of jump out to us at this point where we can trap, we can trap x from 0 to 1, right? So I could say, let's let x go from 0 to 1. What do I want to let y go from? Well, if I let y go from 0, and then I let it go all the way up until we hit this line, which, since this is the point 0, 0, and this right here is the point 1, 1, this is going to be the line y equals x. Our upper bound for y is just going to be x. So what are we dealing with so far? We're basically just now at the point where we have this double integral where x goes from 0 to 1, y goes from 0 to x, of the square root of 4x squared plus 5 dy dx. Okay, this, I would argue, is the most important place to be. If you can get here, a computer program can solve this for you, and it's not the end of the world. Okay, but since this is a calculus class, it's a good idea for us to practice. So let's go ahead and I will do this one with us. So first to bat, dy. I don't see any y's in here, so we treat that as a constant, and so we just get the integral from 0 to 1 of the square root of 4x squared plus 5 with a y on the outside because we do the integral with respect to y. We are going to evaluate it from 0 to x, and then we'll do our dx at the very end here. So let's finish tackling this inside part right here. This inside part is just going to end up becoming the square root of 4x squared plus 5 with an x on the outside. And there's no 0 part because when you plug in 0, it just is going to evaporate. And so now we have integral 0 to 1 dx. And from here, as terrible as this might look, this is actually pretty simple. We can do a u substitution. We let u equal to 4x squared plus 5. And du is equal to 8x dx, which means that du over 8x is equal to dx. And so this is going to lead us to an integral of 1/8 the square root of u du, which the square root of u, this is the same thing as u to the 1/2. So doing the antiderivative there, we're going to get 1/8, and then u to the 1/2 is going to be u to the 3/2 divided by 3/2, so that'll be 2/3 u to the 3/2. And now we need to go back because we need to evaluate this at our bounds. So this is 1/8 times 2/3 times, what was u equal to? Well, u was equal to 4x squared plus 5. And then we evaluate this from 0 to 1 as well. So let's see, what are we going to get? We get 2 over 27. Oh, to the 3/2, right? We're missing the to the 3/2 bit. 3/2. All right. Oops. No, stop. What's going on? Come back. There we go. Sorry about that. So what's happening here? We're just going to plug in our bounds now, and we should be done with this problem. So we're going to plug in 1, and I believe 4 plus 5 is 9, so we get times 9 to the 3/2. And then minus, what do we get when we plug in 0? We get 5 to the 3/2, right? Something like this. Now we can simplify this a little bit, I think, because 9 to the 3/2, that's the same thing as the square root of 9 cubed, which is the same thing as, well, 9 times the square root of 9, which is just 27. So our first one looks like this term right here is just 27. The second one, let's see. So we're going to get this equals 2 over 27 times 27 minus, now let's do 5 to the 3/2. So this is the square root of 5 cubed, which is 5 square root 5. So we'll put 5 square root 5 in here. And this is an acceptable answer. You could leave it like this. You could go one step further and say this is 2 minus 10 root 5 over 27. Either one of these would work. And yeah, they're nasty numbers, but in reality, most of math that you do results in nasty numbers. And what does this number represent? Well, if our units were that this would be in square feet, then this would represent the square footage of, you know, whatever the surface area is that we were trying to calculate in the first place. So you can do this for all sorts of shapes over all sorts of regions, and in your homework you'll get the opportunity to explore that. But this is surface area. This is surface area of a 3D shape. And I know right now it kind of seems in this class like maybe things aren't really coming together, but I promise that this notion of doing double integrals to calculate values over a region of integration will come up very soon again. This idea of calculating surface area, and especially this cross product notation of vectors, will definitely come back very soon. So we're trying to ease you into these ideas without throwing too many down your throat at once. So hopefully this is bite-sized and digestible. And starting in next week's videos, we're going to get to work with triple integrals, which is very exciting stuff. Pretty natural extension of what we've been doing so far. So I will see you all in the next videos.